Welcome everyone to AI Mavericks, the podcast where we explore the cutting edge of artificial intelligence from both the boardroom and the server room. Today, we're diving into something truly fascinating, achieving powerful AI reasoning without breaking the bank.
Thanks for having me. This is a topic that's top of mind for every business leader looking at AI adoption. The sticker shock on some of these advanced capabilities can be, well, significant.
Absolutely. Traditionally, getting language models to perform complex, multi-step reasoning, especially using reinforcement learning or RL, has been notoriously compute-heavy and expensive. We're talking massive GPU clusters, long training times.
So the multi-million-dollar question, sometimes literally, is, can we get that sophisticated reasoning power more cost-effectively? And that brings us to a really intriguing development called TINA. Expert 1, can you unpack this concept for us?
Sure, TINA stands for Tiny Reasoning Models via LoRA. The core idea is deliberate minimalism. Instead of starting with a behemoth 70 billion parameter model, TINA starts small, specifically with a 1.5 billion parameter base model, the deep CCAR 1 distill QN model.
Okay, tiny base model, that makes sense for cost, but how do you get the reasoning boost?
That's where the second part comes in, parameter-efficient fine-tuning using LoRA or low-rank adaptation during the reinforcement learning phase. Think of LoRA like, instead of completely rebuilding a car's engine for more power, you're adding a highly optimized small performance chip that targets specific aspects.
Exactly, LoRA modifies only a tiny fraction of the model's parameters. We're talking about adding and training low-rank matrices that represent the change needed, rather than retraining all the existing weights. It's incredibly efficient.
And this efficiency translates directly to the bottom line, right? Lower compute means lower cloud bills, faster iteration cycles, potentially opening up advanced AI to companies that previously thought it was out of reach.
So a small model plus this efficient LoRa tuning during RL. Expert 3, you mentioned the practical side. How minimal are we talking in terms of setup?
It's pretty remarkable, actually. The TINA experiments were run primarily on just two GPUs, NVIDIA L40S specifically. They even managed to co-locate the RL training process and the inference engine, VLLM, on those same two GPUs by carefully managing memory.
2 GPUs for state-of-the-art reasoning RL. That sounds almost unbelievable compared to the usual narratives.
Well, it takes clever engineering, but yes, and we're not talking about weeks of training either. The process was highly efficient, with RL steps completing quickly. The paper estimates the cost to reproduce their best model checkpoint was just $9 USD.
$9, let me repeat that for the business leaders listening. $9. That's less than lunch for one person in many cities, compared to the hundreds of thousands or millions often associated with training large models from scratch or doing extensive fine-tuning. This is a different ballpark entirely. It's like comparing the cost of a bicycle to a spaceship.
Okay, the cost savings are staggering, but the crucial question remains, does it actually perform? Are we sacrificing capability for cost? Expert 4, what did the results show?
That's the most surprising part. The TINA models weren't just cheaper, they performed exceptionally well. They were competitive with, and in some cases surpassed, the performance of state-of-the-art baseline models that used the same 1.5B base model, but were trained using traditional, expensive full-parameter reinforcement learning.
Surpass them. How is that possible?
Take the AIME24 benchmark, a tough set of high school math competition problems. The best TINA model achieved over 43% pass at 1 accuracy, which was a greater than 20% performance increase compared to the full-parameter tuned baseline on the same base model. Across a suite of reasoning benchmarks, AIME, AMC, Math 500, GPQA, Minerva, the TINA models consistently held their own or outperformed.
And this wasn't just a fluke on one dataset. We saw consistent strong performance across different setups, using data from projects like Still3, DeepScaler, and OpenRS, but applying the LoRA-based RL method.
From a strategic perspective, this is huge. It suggests that the assumption, bigger model plus more training equals better reasoning, might be too simplistic, especially when cost is a factor. There might be smarter, more targeted ways to achieve these capabilities. It lowers the barrier to entry for innovation.
This really challenges conventional wisdom. So, why does this minimalist approach work so well? What's the theory behind LoRa's effectiveness here? Expert 4, the paper proposes a specific hypothesis.
Yes, the rapid format adaptation hypothesis. The core idea is that for reasoning tasks, especially those trained with RL using verifiable rewards, a significant part of the learning involves getting the model to output its reasoning in a specific, structured format, like a step-by-step chain of thought.
Okay, so the format matters.
Critically, the hypothesis posits that LoRa is exceptionally good at rapidly adapting the model to generate outputs in this rewarded format using very few parameter changes. Crucially, because LoRa modifies so little, it largely preserves the vast knowledge already embedded in the pre-trained base model.
Think of it like this: the base model already knows a lot of math facts, scientific concepts, etc. LoRa isn't reteaching it that knowledge. It's teaching it how to structure and present that knowledge in the form of a logical, step-by-step argument that the RL reward function recognizes as correct. It's like teaching a knowledgeable person how to write a well-structured essay, rather than teaching them the subject matter from scratch.
That's a great analogy. Is there data to back this hypothesis up?
There are a couple of interesting pieces of evidence in the paper. First, they plotted reasoning performance against the approximate training compute flops. For the TINA models using LoRa, they observed that less compute often correlated with better performance up to a point. This is the opposite of what you'd typically expect with full parameter tuning, where more compute usually leads to better results, at least initially.
That less is more finding is quite counterintuitive, but supports the idea that LoRa is doing something fundamentally different and more efficient than just brute force retraining.
The second piece of evidence comes from analyzing the training dynamics. When looking at the reward signals during RL training, they saw a sort of phase transition. The reward related to the format of the output, e.g., adhering to structure, desired length, would often peak or become unstable around a certain point in training.
A turning point.
Exactly, but the reward related to the final accuracy of the answer didn't necessarily show the same sharp transition. And interestingly, the best performing model checkpoint, the one with the highest accuracy on held out tests, often occurred just before or around this format-related turning point.
This suggests LoRa quickly masters the required output format. Pushing further on just format optimization after that point doesn't necessarily improve reasoning accuracy and might even hurt it, perhaps by making the model too rigid or verbose terse. It reinforces the idea that LoRa's strength here is efficient structural adaptation while leveraging existing knowledge.
Fascinating. Let's pivot to the practical side. Expert 5, as someone leading tech teams, what does this mean for deploying AI reasoning in the real world?
Well, first off, it's incredibly exciting. The potential to embed sophisticated reasoning into applications where it was previously cost prohibitive is a game changer. Think smaller scale recommendation engines needing deeper user understanding, or internal tools for complex data analysis, or even enhancing chatbots to handle more complex queries without needing a massive backend model.
But are there catches? What are the immediate questions or challenges that come to mind?
Absolutely, the big one is scalability and transferability. These results are on a 1.5B parameter model, primarily focused on math and logic tasks. How well does this LoRa-based RL approach scale to, say, a 7B or 13B parameter model? Does it still provide that massive cost-performance advantage? And how well do these learned reasoning skills transfer to other domains like coding, creative writing, or complex planning scenarios?
Those are key research questions. The ablation studies in the paper give some hints, though. They found, for instance, that dataset quality seemed more important than sheer quantity. A model trained on just 7K curated examples outperformed one trained on nearly 94K examples. That reinforces the smart training idea.
They also found robustness in the LoRa configuration. Ranks like 16 or 32 worked very well, meaning you don't need a huge number of LoRa parameters. Rank 16 slightly outperformed rank 32 in one test, further emphasizing that more isn't always better here.
And they briefly compared RL algorithms, finding Dr. GRPO might reach peak performance faster than standard GRPO, hinting at further potential efficiency gains. Plus, the open sourcing of code, models, and logs is huge for reproducibility and letting others build on this.
Okay, the potential is clear, but there are open questions. Now, I want to introduce a bit of a curveball. We have another expert joining us, Expert 6, who sometimes likes to play devil's advocate. Expert 6, while this efficiency is impressive, are there potential downsides or alternative perspectives we're missing?
Thanks for having me. Look, the cost savings are undeniable and democratizing access is fantastic. But I have a nagging question about the core hypothesis, the idea that LoRa primarily adapts format while preserving base model knowledge. What if preserving all that base knowledge isn't actually desirable?
Go on, what do you mean?
Base models, even distilled ones, can have inherent biases, limitations, or even generate unsafe content patterns learned during pre-training. If LoRa is only lightly touching the model, primarily focusing on output structure, does it effectively address those deeper issues? Full parameter fine-tuning, while expensive, allows for more extensive rewriting of the model's internal representations.
That's a very valid point. Parameter-efficient methods generally trade off adaptivity for efficiency. While LoRa seems highly effective for the format of reasoning here, its ability to fundamentally alter deeply ingrained knowledge or behaviors from the base model is likely less than full fine-tuning. It's a trade-off.
And building on that, does this preserve knowledge, adapt format approach hit a ceiling when faced with problems requiring fundamentally new connections or synthesis of knowledge, rather than just structuring existing information? For truly novel, complex scientific discovery, for instance, maybe the deeper learning facilitated by full fine-tuning is necessary.
This highlights the need for context. For many business applications where you need reliable reasoning within known domains, Tina's approach could be revolutionary due to the cost-benefit. But for cutting-edge research or safety-critical applications requiring deep model reshaping, the calculus might be different. It's not a one-size-fits-all solution, but rather a powerful new tool in the toolbox.
Expert 3, are you sure the researchers didn't just invent this $9 training cost to make the rest of us feel bad about our cloud bills?
Well, the logs and costs are open, so you can check their math. But seriously, it underscores how much potential there is in optimizing the process, not just scaling the hardware and model size. It's a testament to clever algorithm design and leveraging existing resources effectively.
It certainly is. As Peter Drucker said, efficiency is doing things right, effectiveness is doing the right things. Tina seems to be aiming for both, doing the reasoning right and doing it in a cost-effective way. So looking ahead, what's next? Where does this research lead? Expert 5.
I think the immediate next steps are clear. Test this LoRa plus RL approach on slightly larger, but still small, models 7B, perhaps 13BC if the efficiency gains hold. Expand the task domains aggressively. Coding is a big one, complex planning, maybe even multimodal reasoning. Can we teach a model to reason about images and text efficiently using this method?
From the business side, the implications are profound. This could truly democratize access to advanced AI reasoning. Startups can now compete in areas previously dominated by giants with huge compute budgets. Enterprises can deploy reasoning capabilities more broadly across their operations. It also signals a potential shift in talent needs. Engineers skilled in PEFT techniques like LoRa and understanding these efficient training paradigms will be increasingly valuable.
And the open nature of this work, the code, the models, the logs being available, is crucial. It allows the entire community to build upon these findings, verify them, and push the boundaries further. It accelerates progress for everyone. As the paper acknowledges, this work builds heavily on prior open-source efforts.
It truly feels like a significant step towards making powerful AI reasoning more accessible and sustainable. We've discussed the Tina approach. using tiny models and efficient LoRa-based reinforcement learning to achieve surprising reasoning performance at a fraction of the traditional cost. We've explored the rapid format adaptation hypothesis, the practical implications, potential challenges, and even some contrarian perspectives.
It really underscores that innovation isn't always about sheer scale. Sometimes, as the saying goes, necessity, in this case, the need for cost-effectiveness, is the mother of invention.
A perfect closing thought. A huge thank you to all our experts today for sharing their insights on this fascinating development. This has been a technically rich and strategically vital conversation.
A pleasure to be here.
Thanks for having us.
Glad to contribute.
Indeed, a stimulating discussion.
My pleasure.
Thanks for letting me stir the pot a bit.
And thank you to our listeners for tuning into AI Mavericks. Join us next time as we continue to explore the frontiers of artificial intelligence. Until then, stay curious. This paper introduces TINA, a family of small reasoning models. Researchers aim to create strong reasoning abilities cost-effectively. TINA models use a small 1.5 billion parameter base model. They apply reinforcement learning to improve reasoning. This is done using a technique called low-rank adaptation, or LoRA. LoRA updates only a very small number of model parameters. This approach makes the training process highly efficient. TINA models achieve reasoning performance competitive with larger models. Some TINA models even surpass state-of-the-art baseline models. This happens despite using the same small base model. The best TINA model showed a greater than 20% performance increase on a math test called AIME24. It achieved 43.3% accuracy on this test. This result cost only an estimated $9 for post-training and evaluation. This represents a massive reduction in computational cost compared to standard methods. The work shows the surprising effectiveness of efficient reinforcement learning via LoRA. Researchers hypothesize LoRA works well by rapidly adapting the model to the structure of reasoning. It quickly learns the format needed for step-by-step answers, rewarded by reinforcement learning. At the same time, LoRA largely preserves the base model's existing knowledge. This focus on format adaptation is likely more efficient than full model training. Training logs show a distinct phase transition related to output format metrics. Optimal reasoning performance often occurs just before this transition point. This supports the idea that LoRA quickly optimizes reasoning format. The project aims to democratize reinforcement learning research for reasoning. Its low cost makes advanced exploration more accessible. Limitations include using a small base model, which may limit peak performance. The evaluation focused mainly on mathematical reasoning tasks. Future work could explore larger models or different reasoning domains.